Okay, so in this lesson, I'm going to be going through the systems, the unit of measurement, which is the SI units. I'm going to be going through Newton's 3 laws of motion, and I'm going to be going through force, gravity, pressure, and strength. At the end, I'll be talking about vectors. So, you should be getting a handout that you're going to follow along with me, and I'm going to answer those things on the board. Now, I will be reading. I appreciate that you can read as well, but sometimes it's helpful to have things read out, and I will add a few points as we go. So, SI units. It is very important to be able to measure the world around us. Science relies on accurate and consistent measurement. Australia and all other nations except the United States have adopted a standard set of measurements known as the what system? What system of measurements do we use?
Metric.
Metric. Okay, prior to the adoption of this system, measurements were based on those that were used by there are people that live in Italy a long time ago. Just a bit louder.
Romans.
Romans, thank you. I just wasn't sure that you said that. Okay, Romans, and they were both inconsistent and complicated. For example, the gallon, a unit of measurement, is a different size in the UK and the US. Now, if I wasn't recording, I'd take some time to show you a 44-gallon drum or a 40-gallon drum. They're the same thing. It's just a different word. So some people call them a 44-gallon drum, some people call them a 40-gallon drum. That's because England and America can't agree on how big a gallon is. Okay. An example of the complicated nature of the system is the mile, which is 1760 yards, 1,760 yards, or I think it's, they say 5 tomatoes, so 5280 feet. I'm not going to even check that because I'm too lazy. I'm pretty sure it's 5280 feet. Now the point is, I had to use 5 tomatoes as a way of remembering that, and I don't live in the imperial system, so for me it's a bit of an unusual number. Okay, it's this many inches, and it makes conversions very difficult. So I'm now going to scroll. If you guys haven't got that, you can see that when we put the video up. Okay, by comparison, the metric system, introduced in 1799, offers a universal standard based originally on a set of agreed objects, and now on the universal properties of light and atoms mostly. You guys can cross that out because what we have a video is, one of the videos that I've included on group chat for this is, you should be filling these in, yeah? Is a video from Veritasium on the world's roundest object, because in 2018, in November of 2018, they agreed finally on a universal standard for the kilogram. And this universal standard of the kilogram is based on electromagnetism. There were some competing ways. So for instance, the CSIRO, which is an Australian scientific organisation working with other organisations around the world, was spent, I'm going to say many euros. I think, I don't want to pick a number because I'm going to be wrong, and it's something that's so easily provable, to try and create the world's roundest object, to have something that weighs exactly 1 kilogram, a perfect crystal of silicon. Okay, that video is well worth watching. Because this was big news last year, when at the time of I'm recording this, there's some further reading you can look at. So for instance, Radiolab has a very interesting podcast that talks about the different SI units, and those links are available there, but they're definitely worth following up. I would show them if I wasn't recording now. So, now all of the units are based on something to do with light or atoms or some other universal property. And the idea for that is because before this came along, what we had is a kilogram that was measured off an object in Paris. And so that if all of the Earth got destroyed by a meteorite or something like that, and they found records of our information, they'd have no way of knowing exactly how heavy a kilogram was. Whereas now, our standard is universal, so it means that anyone in the universe could be able to reproduce that same definition of a kilogram based on a technical definition. Okay, The system is also simplified as all units are based on seven base units. If I show you here, so if I go to the SI units, you can see there are 7 base SI units. We're only interested in these 3 here, at least for this part of the course. Eventually we'll talk about amps. We do also talk about K, which is for temperature. We'll talk about that in a second. So the main ones that we're interested in the world of engineering is we're mostly interested in the kilogram, the meter, and the second, which we'll talk about in a second. Okay. You can see that they're all linked in that they have a, somewhere down here they show where they're all linked, but I can't be bothered finding that now, so we're just going to keep going. 7 base units. The larger or smaller units are multiples of 10 of these units. For example, the something is 1,000 times larger than a kilogram. What's something that's 1,000 times larger than a kilogram? Ton is exactly right. Now, is it spelt like that, or is it spelt like that?
Second one.
The second one, because it's got 2 ends like Napoleon. Napoleon was around when the metric system was being introduced. If that, maybe that doesn't help you, I don't know. We're using the double N, ton, T-O-N-N-E, ton. The ton is 1,000 times larger than the kilogram. Okay, technically, the official measurements in Australia and most nations is the International System of Units, or SI units. And the reason why it's reversed letters is because in French the letters are reversed. It's the Système International d'Unité. Published in 1960. Not all metric units are SI units. For instance, the ton is a metric unit, but it's not an SI unit. And other examples are the litre. The litre is not the SI unit for volume. What do you think the SI unit for volume is? I'll give you a clue. It's something to do with a metre. The measurement for area is the metre squared. What do you think the measurement for volume might be? The metre cubed. Thank you. Okay. Instead we use the cubic metre. It's literally written there. Okay. Both measure volume, but only the cubic metre is an SI unit. Other units, such as the ton and hectare, are metric units, but they are not SI units. So instead of hectare, we should be using metres squared. We still use hectares because they're useful, but they're not SI units. Now, similarly, for measurements for time other than seconds, minutes, hours, they're not SI units. So in the SI units, we only ever use seconds. Now, I'll mention it here because we will mention it later. Celsius is a metric unit, but it is not the unit that the SI unit. The SI unit is something else called Kelvin, which we'll talk about later. Okay. All units measured in this course derive from 3 of the base SI units, which are, I just said them. Can anyone remember? I circled them. KMS units, we sometimes call them. Okay, what's the one for distance? Meter, thank you. All right, so in Commonwealth countries it's spelled RE. Yeah? A meter with an ER is something that measures, like a odometer or something like that. That's spelled ER. Okay. So we have the meter. What's the one for weight? Kilogram. And what's the one for time? Second. Okay, other units, such as the gram and kilometre, are multiples of these units, usually denoted by a prefix. Now, we're all familiar with millimetres and millilitres. Yeah, so we're familiar with milli. Milli comes from the French word mille, which is French for 1,000th. Kilo comes from the Greek for 1,000. We're all familiar with kilometres and kilograms. Megameters and megagrams, we don't tend to talk about those as much, right? We don't tend to talk about megameters and megagrams. We do talk about some other units which have a mega in them. What is a term that we might be more familiar with that has to do with mega? What would MB stand for? or GB, or TB?
Megabyte, gigabyte.
Excellent. Megabyte, gigabyte, and terabyte. That is exactly right. Thank you for that. Okay. Please note the kilogram, not the gram, is the base SI unit for mass. The base SI unit for mass is the kilogram, not the gram. Why? Well, if we go back to this video that I talked about, originally it was called the graph.
They wanted to measure anyway, and so they settled on a gram, which was just 1,000th of a grav. But soon they realized that a gram was too small, and so they returned to the grav. But since they couldn't call it that, they invented the kilogram, 1,000 gram.
Okay, now this really irritates me, right? This really irritates me. If I rule the world, I'm going to change it to the Z, right? I'm going to come up with my own unit of measurement, right? But we're a little way off that, so don't worry about that too much. It won't be in the test. Not yet, anyway. Okay, so we're going to go to here. Other units, such as the unit for force. I'm going to tell you what the unit for force is now. Ready? The unit for force is the Newton. It's named after the scientist who talks about apples. The new... Got that wrong? Not the net one. The Newton. Pressure is the Pascal. Again, I'm speaking to him. Pascal. And other units such as the unit for volume. What did we say the unit for volume was?
Meters cubed.
Meters cubed, thank you. Or acceleration, they're based on combinations of those three units. We'll learn about that as we go. Okay. Newton's three laws of motions. There are three fundamental laws of physics that describe classical mechanics. Now, you might have heard of quantum theory and relativity, but they're not things that we talk about in this course. I'm happy to go into them at a later date, but the idea is that quantum theory applies to the very, very small, the atomic level, and relativity is where we're talking about planets and stars and galaxies. But for the world that we live in, we can get away with what we call classical mechanics, classical physics. Now, there is some complications, but for the moment that will be all we will ever need in a high school level physics. Okay, there are three laws. The first law says an object at motion will remain in motion, and an object at rest will remain at rest until acted on by another force. Now, I have some videos from the 80s that I remember watching when I was a kid, before I was even in high school, because my mum's a science teacher and, you know, she wanted to test it out on me. These videos here called Eureka. They're made by the Canadian government in the 80s, and these videos, that I think they are very, very good at explaining the Newton's three laws. Now, if you go to the first of these videos, which we can't even see the first one here, I've created a link, and normally I will show these, but I'm going to go through the document first, and we're going to come back over it. So, what they talk about is in the first one's called Inertia. And it talks about inertia, and it says that objects are lazy. All the objects in the universe want to keep doing, well, anything that's not living wants to keep doing what they're already doing. So let's read. All non-living objects could be described as lazy. Don't write that in a test, because they're not alive, and that will lose you marks. But another word for this concept is inertia. A rock will not start moving for no reason. If the rock were rolling down a hill, the rock would not stop until it hits the bottom or something else blocks it. You might consider a ball rolling on glass will eventually slow down and stop, but this is due to friction of the ground and the resistance of the air. Without friction, which includes wind resistance, an object moving through space will continue to do so forever. So if you were to throw a rock and it gets into space, it will continue to move forever until it stops, until it gets sucked into the gravity of a star or something else acts upon it, it will continue to go forever. Now, it is as difficult to make an object start moving as it is to make it stop. Now you see this when you have people on ice, when people are driving on ice, or if you have ice skating. If any of you have ever gone ice skating or roller skating, you might realize it is very hard to make yourself stop. You need to use some sort of friction. You need to use brakes to make yourself stop. So you need to use a force to cause yourself to stop. Often, larger objects are harder to make start or stop moving than smaller ones, but not always. A large cube of styrofoam is much easier to move than a small cube of lead. The relative ease of an object to start or stop moving is measured by its inertia, or its measure of inertia, which is called its mass. And the mass of an object is measured in what unit? What is the unit that mass is measured in? It's written on the board. I'm about to circle it. Could someone offer it? Just a little bit louder. So thank you very much. The kilogram. Mass is measured in kilograms. Okay. It's a bit odd. You might think that, oh, I didn't think mass was measured in kilograms. But we'll come back to that. Okay. The second law. The second law, because it's a law, I'm going to say it in a big voice. The force of an object is equal to the product, that means times. Sorry, we'll say that again. The force of an object is equal to the product of its mass and acceleration. Or, how most people say this is F, so force equals mass times acceleration. That's what most people will say. Force equals mass times acceleration. That is a easy way to say what I said. I just used fancier words. Okay, the same amount of effort will move a ball of great mass. Let's say I have a 10 kilogram cannonball, right? And I also have a smaller ball that weighs 1 kilogram, like a cricket ball, right? And the cricket ball is not 1 kilogram, but we'll run with it for the moment. Let's say I have my cannonball and my very heavy cricket ball. However, the heavy ball will move faster or slower than light one? If I push a heavy ball and a light ball with the same amount of force, which one do you think will move faster? The small one. Okay, so we're going to say the heavier ball will move slower than the light one. Okay, because of the force law, the first law, we're not interested in the final speed. We don't care about the final speed of the object. What we're interested in is how quickly it reaches its final speed. We're interested in the change in speed, or its, when we measure the change in speed, what do we call that? Acceleration. Excellent. Okay. Now, technically, that's its rate of change of speed. Now, does acceleration have one C or two? Okay, let's hope that's spelled right. I'm about to rub it off anyway. So, okay, the reverse is also true. When a ball hits a wall, it very quickly decelerates. If a heavy ball and a light ball both hit the wall at the same speed, the force needed to stop the heavy ball is much greater, that should say, than to stop the lighter ball. Okay. It's only one L, there we go. Okay. Acceleration is equal to the change in speed divided by time. Now, the change in speed divided by time. And now, a way that we like to say the change in speed is we like to say the delta speed. Now, delta is a Greek letter, and we can just remember that as delta speed just means the change in speed. It's just a symbol for saying the change. So what we could do is we could take the final speed minus the starting speed, and that will give us our change in speed. Consider a model train. Now let's say we had a train, and the train weighed 1 kilogram, or it had a mass of 1 kilogram rather. That can reach its top speed, 36 kilometers per hour, in 10 seconds. Well, first of all, we don't like kilometers and we don't like hours. So what we have to do is we have to convert kilometers and hours into meters and seconds. So if there's 36 kilometers, that means there's 36,000 meters, right? And how many seconds are there? Well, in an hour there's 60 minutes and 60 seconds. So how many seconds are there in an hour? 3,600, thank you. Okay, so, because I've chosen nice convenient numbers, what is the speed of the train? What's its highest speed? The fastest speed this train can go is what? 10 meters per second. 36 kilometers per hour or 10 meters per second. Now, if the train took 10 seconds to reach that speed, you know how you talk about, you see cars have to reach their top speed, yeah? So a lot of the time when you sell a car, you're interested in how fast it can reach 100 kilometers per hour. This is a similar idea. I'm going to come back to that idea in a second, but this is a similar idea. Okay, the train took 10 seconds to change its speed to go from 0 to 10 meters per second. Yeah. Now, therefore, its acceleration is its change in speed, 10, divided by 10, which is 1 meter per second. 1 meter per second per second. Now, this means that for each second, the train's speed increased by 1 meter per second. Now, again, I'm going to go back to, in the Eureka videos, if you watch this Eureka video, Program 5, Acceleration 2, it is a really good video that clearly explains what I'm talking about. It uses an example and a demonstration of what I'm talking about. So I'm going to suggest that you watch that video if you're not sure what I'm going on about at the moment and come back. But I'm going to press on for a second and I'm going to say, okay, imagine our train. Choo choo, the train leaves the station. At 0 seconds, it's gone 0 meters. That makes sense. Now, in the first second, it's gone 1 meter. It's 1 meter away from the train station. In the next second, it's 3 meters away. And then it's 6 meters away. Then it's 10 meters, 15, 21 meters away from the train station. 28 meters from the train station. 36, 45, and then finally, in 10 seconds, it's 55 meters away from the train station. Now, let's consider how much distance did it actually, if we were to measure the distance it travelled just each second, the change in distance, the delta distance, in that first second was 1 meter. Then 2, then 3, then 4, then 5, then 6, then 7, then 8, then 9, then 10. So we can see that each second it's going a little bit further than it did in the previous second. So we would say its speed was 1 meter per second. It went 1 meter in that second. That makes sense. In the next second it went 2 meters in 1 second. The next time it went 3 meters. How long did it take? 1 second. The next second it went 4 meters. How many seconds did it take?
4 seconds.
1 second. So it's going 4 meters per second. The next time it went, Tom, it went 5 meters. How long did it take? 1 second. The next time it went 6 meters. Tom, how many seconds did it take?
1.
1. So it's going 6 meters per second until eventually it gets final speed, choo choo, it's going 10 meters every second after that. It keeps going 10 meters, 10 meters, 10 meters, 10 meters until it gets to the next train station, or until it starts slowing down. Okay, now, Tom, what we want to look at now is what was its change in speed? What was the change in speed from here to here? How much did the change in speed change? 1 meter per second, exactly right. It changed by 1 meter per second in that second. The next time, what was its change? 1 meter per second. And then the next time it went up by 1 meter per second. It keeps going up every time by 1 meter per second. You could say its change is 1 meter per second every second. Is that right? You happy with that? Okay. It's increasing its speed by 1 meter per second every second. So, therefore, the train's acceleration can be described as, Tom, this is all you.
Oh.
Describe that change in speed. It was what?
1 meter.
1 meter per
second.
But how often did it increase?
Every second.
Every second. 1 meter per second every second. Yeah? Its change in speed was that's its speed, got bigger by 1 meter every second. The SI unit can be written in various ways, and in this course, I will usually write it as 1 meter per second squared, like that. But if you do iSTEM, the science teacher, he might write 1 meter per second to the -2, right? So the thing we could say is 1 meter per second, or 1 meter every second. We tend to say 1 meter per second, or 1 meter per second squared, or if you're in science, in physics, they write it this way: 1 meter second to the negative 2. Now, a little bit ago, we learnt about the second law. Can anyone tell me what Newton's second law was? Can you remind me? It was 3 letters. Okay. I'm going to show you a picture to help you remember. Force is equal to... The second law of physics is force is equal to...
Mass times acceleration.
Force equals mass times acceleration. F equals ma. Force equals mass times acceleration. Yeah? So, what is the measurement for force? A force of 1 kilogram accelerating at 1 meter per second is called a... What do we think the N stands for? A Newton. Now, I got this wrong just this year, that Newton is spelt with a little n, but the symbol is a big N. Because anything that's named after a human, the symbol is a big letter. Meter is not named after a human, so it's a little letter. But Newton and Pascal are both named after humans. Kelvin, is, so they're all written with capital letters when we write the number. Okay, the third law. Now, you will have heard this law before, right? You hear people say this a lot. For every action, there is an equal and opposite
Reaction.
You guys knew it. I didn't even have to say it. For every law, there's an equal and opposite reaction. Now, here's what we're going to do. We're going to imagine that you had a cannon. Now, a cannon weighs 1,000 kilograms. What do we call that?
1 ton.
1 ton. Thank you very much. For every, we have a cannon, it weighs 1 ton. It accelerates a ball at a 10 kilogram ball, a cannonball, at an acceleration of 20 meters per second squared. The cannon will recoil in the opposite direction. So the cannonball goes this way, right? And then if the cannon's ball is going that way, what has to happen to the cannon?
Goes the other way.
Yeah. Does anyone know what that's called? When you have a gun that it forces the force back into your arm? What's that called? Recoil. That's exactly right. The cannon will recoil in the opposite direction. The force of both the cannon and the cannonball is 2,000 newtons. Let's have a look at that. Here, the cannonball has a force equals mass times acceleration. The mass, we said the cannonball weighed how much? It had a mass of how much? What was the mass of the cannonball?
10.
10. And how fast is it accelerating?
200 meters per second.
200 meters per second. So what's 10 times 200?
2,000.
2,000. What do we call a Newton multiplied by a kilogram? Sorry, I just said the answer in my question. I'm sorry about that. What's the force is measured in what units? It's named after the guy the apple fell on.
Newton.
Newton. So I write 2,000 newtons. Now, on the other side, what is the force that the cannon is going to shoot backwards? What's its force? Its force has to be equal. So what's its force going to be equal to? The two forces have to be equal. What's the other force going to be? 2,000. 2,000 newtons going in the opposite direction. How heavy is the cannon? What is the mass of the cannon?
1 ton.
1 ton. Okay, so what we're saying is 2,000 equals mass of 1 ton multiplied by what acceleration? What's that number there? What number needs to go in there for that equation to be true? Anyone else?
4.
No, you had it. I just want to say it louder.
2.
2. Thank you. Okay, 2. So the acceleration of the cannon is 2 meters per second squared. Now, I wrote here something that's incorrect. I said that the cannon will continue to accelerate until it's acted upon by another force. It won't continue to accelerate. It will continue to, it'll actually decelerate because of friction and things. It will continue to move. Yeah? So if you want to cross that out, you can write move. It'll continue to move, not accelerate. Luckily I teach this subject with a physics teacher, and he corrected me and he said that actually that one's wrong. So, it will continue to move until it's acted upon by another force. Okay, can you see how the forces here on each side are equal? The cannon is moving back, but it's moving back at a much slower acceleration compared to the cannonball, which is moving at a much higher acceleration, but they both have the same force. Okay. Okay. Often, the cannon will only accelerate for less than a second, will only continue to move for less than a second as the friction of the ground resists the force of the recoil. It is possible to fix a cannon so it will not recoil or accelerate at all, but by positioning in front of a wall. What would happen if you put a cannon in front of a wall? What would be the worst thing that could happen if you put a cannon in front of a wall?
The wall would blow up.
Yeah, it might break the wall, right? So if we put it in front of a wall, when the cannon fires, the force of the wall, the force will force the recoil will be completely absorbed by the wall. Sorry. When the cannon fires, the force of the wall will be completely absorbed by the wall. In this case, the reaction force, this is that reaction. Every force has an equal and opposite reaction. The reaction force of the wall is equal to the force of the recoil. The wall can take that force. It can absorb that amount of force. It can provide a reaction force that is big enough for it to not break. But it is also possible that the reaction force needed is so big that the wall can't produce that much force. And it will break, it will fail. It is the job of engineers to design structures to ensure that they are strong enough to provide sufficient reaction to withstand failure. I'm going to say that sentence again. I'm going to say it one more time afterwards in a simpler way. It is the job of engineers, what engineers do as their job, is to design structures, right, to think about how big the structure needs to be, to make sure or ensure that they are strong enough. So engineers design structures that are strong enough, that they provide sufficient reaction force, so that engineers design structures that are strong enough that they can give back enough force to withstand failure. Engineers design things big enough and strong enough that they don't break when they need to provide reaction forces. Okay. Gravity. All objects on Earth are forced downwards by an acceleration called gravity. Okay. In theory, all objects fall at the same acceleration. But this isn't always observed. So if I drop this tissue and this pen, do you think they'll fall at the same rate?
No.
Yes.
Well, okay, that was a bad test because I didn't release the tissue at the right time. Let's try it one more time.
The air resistance.
Air resistance. Now, I have a couple of videos here where we can look at that, where we can see I've updated this more recently than I'd like. Okay, so this video here, we can see a vacuum chamber. If we release these two objects in a vacuum chamber, they do fall at exactly the same rate. If we eliminate the air resistance, they do fall at the same rate. And because there's no air on the moon, you can also watch astronauts on one of the Apollo missions dropping a hammer and a feather at the same time, and again we see that they fall at exactly the same rate. The picture is not very clear, so I'm not going to go into it this lesson, but I will talk about it at a later date. Okay. So, in theory, everything falls at the same rate if we ignore wind resistance. Now, when we ignore wind resistance, we find that everything falls at an acceleration of 9.8 meters per second squared. Now, in engineering, not in physics, you're allowed to say 10 meters per second squared, right? You're allowed to say that. Real engineers don't use that because we need that 2%. If you design everything 2% too strong, no one will work with you. No one will want to hire you because you're going to be too expensive. But in our HSC course, we're allowed to use 10 because it's just easier, right? But if you want to remember the exact number, and this will help you for physics maybe, I have a song based on Alicia Keys that she talks about falling, and Alicia starts with A, and gravity is an acceleration. So we could say A is equal to 9.8 meters per second. Keep on falling at 9.8 meters per second squared. I don't have anything for the second line. Okay. I'll do it one more time. I'll give you the soundbite one more time.
Oh, we finished.
I keep on falling at 9.8 meters per second squared.
Yes, sir. So you got coming to that second line.
So can you do that?
Can you sing that? Yes, sir.
Okay, so, okay, ready, this one here, we've got another song coming up real soon.
Oh my gosh, yay.
Something is the term for the force of gravity. It starts with a W.
Wait.
Wait!
Oh.
Wait for it.
Oh.
Bad puns, that's what I'm here for, right? They call me the bad puns. Okay, so I have a song about that as well.
Yes.
And that will probably be where we end for today,
You're gonna
I
sing
think.
this one as well?
Yeah, okay, but I'll probably turn it off. I will just find us the song and then I'll go from there. Because I've lost it now. Weight versus mass song, where is that?
Oh my gosh.
Okay, so the link is not there. That's a pain.
Just look it up.
Okay, I will just find it on YouTube, but I'm going to press pause now, and I'm just going to find. So if you look up the weight versus mass song, you'll be able